This is an overview of Chapter 3 on the derivative for those of you that need a little extra explanation of what we've covered in Chapter 3. I've divided this up into just a few parts. The first part is on the limit of a function. This here is an example of a function if I make this so we have an open circle here. Because remember, a function must pass the vertical line test. And then for this part of the graph, there's a dot. So this is a piecewise function, and it keeps on going in both directions, to the left and to the right. We're going to find limits for this graph that's given. I'm going to first work with a graph and then with an equation. Let's find. And the first one is the limit of f of x as x approaches -1 from the left. This little negative sign up there means from the left. And if we're coming from the left, what is the y value that is being approached? Well, that would be 1. So this is equal to 1. Number 2, find the limit of f of x, and this whole function is f of x, this graph, as x approaches -1 from the right. Well, if we're going from the right, going towards -1, do you see how the y value is 1? So this is equal to 1 also. If we generalize this and find the limit of f of x as x approaches -1, this means from both the left and from the right, since they both equal 1, then the limit as x approaches -1 is 1. Let's look at some others. Number 4, the limit of f of x as x approaches 0 from the left. Going towards 0 from the left, what is the y value that's being approached? Well, that's 0. Number 5, find the limit of f of x as x approaches 0 from the right. Well, that's going to be in this part of the graph up here. So approaching 0 from the right, do you see how the y value is getting really close to 2? When you're finding a limit, it doesn't matter what happens exactly at that point. So if you look at number 4, see how it's 0 from the left? Even though there's an open circle there, it's okay because we're just looking at values of y that get really close to 0. But it doesn't matter what happens exactly at that point. And then here for number 5, we're finding the limit of f of x as x approaches 0 from the right. It does hit the 2, but it doesn't matter. If there was an open circle there, the limit would still be the same. Find the limit of f of x as x approaches 0. Well, if we look at numbers 4 and 5, do you see how number 4, from the left it's 0. If it's approaching 0 from the right, it's 2. Since these numbers are not the same, then it does not exist. It needs to be going to the same number from both sides. Let's look at some examples of equations. Let's find the limit of 2x minus 5 as x approaches 3. For this one, we can plug in the 3 into this x here, so we have 2 times 3 minus 5, and this is equal to 6 minus 5, which is 1. If we think about what the graph looks like, y equals 2x minus 5 is a straight line, and as x gets really close to 3, then y approaches 1. And you can see in the 1 is a straight line, there are no breaks or anything, and so y approaches 1 from the left and from the right of 3. But let's look at one that's a little more difficult. Number 2, find the limit of x squared plus 5x minus 6 over x minus 1 as x approaches 1. You see a problem with this one. If we try to plug in 1 for x in the denominator, we're going to get 0. And so what we can try to do is simplify this and then find the limit. If we take the limit as x approaches 1 and factor the numerator, we have x plus 6 times x minus 1, because factors of -6 that add up to 5 are 6 and -1. And then we can divide out the x minus 1s. So now we have the limit of x plus 6 as x approaches 1, and we can plug in the 1. I noticed for several of you on the homework and the review that you were dividing the numerator and denominator by x. You're only going to do that when you're finding the limit as x approaches infinity or negative infinity. Let's go on to infinity. So limits at infinity. For this part, we're also going to look at a graph and an equation, and you also saw tables in your notes. You can refer to the tables there. I'm just going to work with the graphs and equations. So suppose that we have x and a y axis, and then these are just 1 unit apart. We have a horizontal asymptote at y equals 2, and then a graph that looks like this. Let's find the limit of f of x, and this graph is f of x as x approaches infinity. For looking at the graph as x approaches infinity, remember this is the x-axis, so as x is getting larger and larger, what is y approaching? And so we come out here, keep going out further and further, and we see that y is getting really close to 2, so this is 2. Now let's find the limit of f of x as x goes to negative infinity. We're going in the negative direction for the x's, so that's this direction. What's happening to the y's as you go further out in the negative direction? You see how y's keep increasing, and they increase indefinitely, and so we go up to infinity. We could also say that this limit does not exist, but writing infinity there is a little more specific. Let's look at equations. The first example of an equation, if we want to find the limit of 1 over x as x approaches infinity, let's just think logically about this. The larger that the denominator gets, the smaller that whole fraction gets. So this is getting closer and closer to 0. And it's the same idea as with a negative. So the limit as x approaches negative infinity of that same function. Well, even if you have 1 over larger and larger negative numbers, the fractions are getting smaller and smaller. Even though they're negative, they're just getting closer and closer to 0. So let's do one more of these. Suppose that we have a limit of 3x squared plus 7 over 8x squared minus 5x, and we're taking this as x approaches infinity. If you remember from the notes, we want to divide all of the fractions by the highest power of x in the denominator. So the highest power of x in the denominator is x squared. We're going to divide every term by x squared, and this will make it easier to find the limit. This is equal to the limit as x goes to infinity, and I'm just going to rewrite all of this, and then underneath each fraction, let's write x squared. That's the highest power of x in the denominator. Let's simplify each fraction. Separately, we've got 3 plus 7 over x squared over 8 minus 5 over x. Now remember that we're going to infinity, so as x gets larger and larger, when you have these little fractions, what happens to these fractions here? This is going to approach 0. And same thing here. As x gets larger and larger, because x is going to infinity, this fraction goes to 0. And so then we're just left with 3 over 8. And then let's go on to continuity. I'm going to draw a graph and then look again at a piecewise function. So a graph, suppose we have f of x, and it has a vertical asymptote at x equal to -1. And then at 2, so at x equals 2, there's a hole. This is f of x, is this piecewise function, so 2 parts. What we're trying to do is find out where is f of x discontinuous. We're just going to write down the x values where you're lifting up your pencil from the paper. Here we have x equals -1, and at x is equal to 2. a lot of times it's easier to label where it's discontinuous rather than where it's continuous. And we're just finding the x values when we're asked to find where it's discontinuous. Let's try another problem where we are given an equation of a function. This is a piecewise function. There are three parts. The first part, f of x is equal to x plus 1 if x is less than 1. It's equal to 2 if 1 is less than or equal to x is less than 4. And it's equal to x minus 1 if x is greater than or equal to 4. To do this problem, we just need to find out what's happening in between. Because if we look at the first one, y is equal to x plus 1 is a straight line. Same thing for y equals 2, it's also a straight line. And then y equals x minus 1 is a straight line. So these are all straight lines, but we need to see if they connect to each other or if they don't. If they don't connect to each other, then we have a point of discontinuity. So the question for this one is also find the x values where it is discontinuous for this function. What I'm going to do is find out what happens at each of these values here, at 1 and at 4. If x is equal to 1, even though it's not included in this first one here, let's just see what happens if it is 1. If x is equal to 1, then we'll have y is equal to 1 plus 1, which is 2. And then do you see for the second part of this, how y is equal to 2? No matter what x is. And since these 2's match, we're not going to have discontinuity. You're going to have one line that's connected to the other. And then for the second part, what if x is equal to 4? Well, if x is equal to 4, looking at the second part of this, we have y is equal to 2. And if x is equal to 4 in the third line segment, we have y is equal to 4 minus 1, which is 3. Now, do you see how the 2 and the 3, these do not match? And since these are not the same, that means that it is discontinuous at x is equal to 4.